All right.
Let's do 7 pi over 10.
Excuse me?
We do 7 pi over 10.
7 pi over 10.
By the reference table. Every way I did it, I got 13 pi over 10, which makes no sense.
All right, so let's. There's a handful of them on here that I think are important to talk about. And I'll just do them on the side here using various. So for my questions, like what is that, 7 to 11 or something like that, is ask you to take a angle theta and find the reference angle that goes with it. So this is the way I think that we should do this. That's 0. This is 2 pi, right? This is pi. Those are the ones I always set up first, and then I rewrite them so that they have the same denominator. It's really hard to compare where 7 pi over 10 is compared to pi, right? But if this is 10 pi over 10, because that's still pi, right? If it's 10 pi over 10, now I know 7 pi over 10 is at least before it, right? Okay? And then I call this 5 pi over 10, because that's halfway in between 0 and 10 pi over 10, right?
Yeah.
So then where's 7 pi over 10 going to stop? This quadrant, right? Now, I don't care how close or how far into that quadrant I make it, but that's my theta that they tell me. Now, remember, theta bar is then how far you need to continue to get to 10 pi.
Is it 3 pi over 10?
3 pi over 10.
I keep forgetting you can't take it to the
You can't go to the y-axis. Nope. Okay. Another one on there was, and this is coming from my questions 10 and 11, something like, say theta is,
negative 0.6.
well, let me just, so negative 1.2 pi. Negative 1.2 pi. Okay, well that means then if I look at this as 0, so it's negative, so now, and you can do one of two things here, guys. I didn't mention this to the last class, but if I've got a negative angle, can I add 2 pi to that to get a positive angle?
Yeah.
And the information about the reference angle, the positive angle or the negative angle is the same. So let's see, we'll do it this way first, directly, and then add 2 pi to it and see if anything really changes. But if that's 0, I'm going to say that this is negative pi now. Does that make sense? Because I'm going to be moving in a clockwise rotation. So negative pi, this will be negative 2 pi. Now this will be negative 1/2 pi. So that's negative 0.5 pi. So instead of putting things in in fraction form, I'm going to put them in decimal form. And leave my pi, obviously, not multiplied through. So now does it make sense that when you draw out theta, there's negative 1 pi, negative 1.2 pi would maybe be about right there? So if that's negative 1.2 pi, how far do you need to go back down there to get to negative pi? How big is it? So we need to retract 0.2 pi.
It's not going to be negative 0.2?
No, your theta bar is always positive. No matter what direction you're moving, either you're going that way or that way, back to the x-axis, theta bar, your reference angle is always positive. Does that make sense? If I did this, let's go, so if I had negative 1.2 pi and add to it 2 pi, okay, because I want to get something between 0 and 2 pi. That's going to give me, what, 0.8 pi? Does that make sense? Okay, so now 0.8 pi, this would be moving counterclockwise. This is 0.5 pi. This is 1 pi. 1.8 pi, stop right there.
Yeah.
And then how far do you need to go to get to there? 0.2 pi. So if you got it, and that's the thing that you can, some people, it's just your way of doing things. You get to make the decision. Do you ever want to deal with a negative angle? It's up to you. If you never want to deal with a negative angle, always add 2 pi to it or 360 to it until it becomes positive. And then you never have to deal with it. Okay? This one here, 1.2. Okay, so what they're doing, saying your theta is 1.2, is saying that's 0. There's no pi here, right?
Yeah.
That means pi has already been multiplied through. So wouldn't that be 3.14 there, approximately? Pi over 2 is approximately 1.57, and 3 pi over 2 is approximately 4.71. So does 1.2 radians make sense that it stops short of that? Short of 1.57?
Yeah.
So we're in the first quadrant, right?
Yeah.
Didn't we say theta was the same thing as theta bar in the first quadrant?
Yeah.
So if we give me 1.2, we're in the first quadrant. That's why 1.2 is that answer. What if so here's the next one. And this is the reason I've been talking about these, because it leads up to this question number 11. And most people that are working on this struggle with part B on number 11. If we're looking at 2.5, so here's the thing, again, 2.5, there's no pi symbol there, right?
Yeah.
Okay, there's no degree symbol, so we know this is right, even though it doesn't say anything there. In the direction says nothing about whether we're in radians or degrees. But because there's no degree symbol, we must assume it's radians, right? Okay, so this is radians. There's no pi there, so pi has already been multiplied together, so it makes sense to look at it this way. Okay, now 2.5, where's 2.5 going to stop? What quadrant? Second quadrant, so 2.5 might be there. Okay, now here's where we get into trouble. If that theta right there is 2.5, and I ask how do I get to theta bar, a lot of people will go, well, theta bar is equal to, because it's in the second quadrant, 3.14 minus 2.5, right? And the answer is 0.64, right? But when I look at 3.14, I approximated that, right?
Yeah.
Okay, I'm just using that to help me recognize where 2.5 should be. 2.5 is exact, 3.14 is approximated. It doesn't tell me anywhere in the problem how to round, correct? So the assumption we want to make, and this is the thing about mathematics, is there's times you got to make assumptions based on the directions. There is no rule for rounding, so it means don't round. So they want an exact answer. So instead of using 3.14, what should I really be using? Pi. And then I take pi minus 2.5, and obviously those are not like terms. One's rational, one's irrational. We leave it that way. Just be on the, I think that's number 11, part B. That's the only one on there, I think. I kind of scrolled through them quickly last period, but I think that's the only one on there that does something like that in this assignment. There will be other situations that come up through other assignments that logic kind of presents itself. Yes.
For the negative 12 pi there, do you just add 2 pi to get like more?
Yeah. So you can do it one of two ways. You can go. So negative 12 pi, we go, well, that would be 1 revolution. That's 2 pi, right? But it was negative 2 pi because I went in that direction, right? There's negative 4 pi, negative 6 pi, negative 8 pi, negative 10 pi, negative 12 pi, right? So negative 12 pi is going to put me right there. Well, there's no angle that I can make there, right? Okay, then my terminating ray is on top of my initial ray, so we say that is 0 radians. Or if you want to go negative 12 pi and just add 2 pi, what ends up being 6 times, doesn't that give me 0? I guess here's the thing, is that we talk about these angles. Did I call these quadrantal angles yesterday?
Yeah.
Okay. There will be situations where your terminating ray does rest on a quadrantal angle. If it rests on the first one, we get a 90-degree angle. Rests on the second one, we get a 180-degree angle. The bottom one would be 300 or 270. But you can come all the way around and be 360. But every time that I look at a 360-degree angle, a 360-degree angle is identical to a 0-degree angle, right?
Yeah.
Okay, so that's kind of what they're looking at there. You guys think that helps a little bit?
Yeah.
Okay. Keep looking at that. Talk about more of those tomorrow if you've got questions tomorrow about it. I want to get it. I want to do at least one more of these here that we did yesterday. Because, go ahead.
So I wrote it down. So you know how like -0.866025 always comes up?
Yeah.
So like, is it a bad way or an okay way if like we just put in like sign of the number and if it gives us that, is it okay that we just remember that number is negative radical 3/2?
I mean, that's a way to do it.
Or is that like?
My fear is that you're going to.
That's what I would do.
You're going to maybe miss out on, if we don't use the special right triangles and that kind of stuff, we might miss out on learning a topic that might be crucial for something later on. I mean, it does work. There's not. I'm not going to say that I've never not done that. Does that make sense? But make sure that you understand how that number is being generated if you're going to use that process. So here we got cotangent 495. Now, cotangent 495 is not a nice number, right? So here's the idea. This is the theta. 495 is theta, okay? But if I can find the cotangent of theta bar, that's going to tell me the same thing, except for the plus or minus aspect, that cotangent 495 is, okay? So the first thing I want to do is think about that angle, and that's outside 0 to 360, right? So let's put that angle inside the range of 0 to 360. So I would subtract 360 from that, right? So we get 135. And it's a cotangent, not cosine. So cotangent 135. So that's still the theta that I'm interested in, okay? Because theta of 495 and theta of 135, they are the same angle, okay? And I'll kind of explain to you maybe in a graph here in a moment that logic. Okay, so then 135 degrees would be over in the second quadrant. You guys agree with that? Okay, so there's theta of 135. Draw this thing down. So here's theta bar, right?
Yeah.
How big is theta bar? I heard it. Somebody say 45? So theta bar, that angle right there, is 45 degrees. So in any 45-90 or 45-45-90 triangle, the legs are both what? They're both in. And then the hypotenuse is in radical 2, right? Now here's, and I like to do this in my picture. I don't usually use all students take calculus directly. I make sure that at the end of every problem that I do, does my answer match that? Do I have the correct sign? But in my picture, I think it makes the most sense to remember that we're in the coordinate plane here. That's what these axes are, right? That point right there is 0, 0. To get to any point over here, don't I need to move left from 0, 0?
Yeah.
So what is the sign that goes with this n? Negative. This y value here is positive, right? And we talked about a radius always being positive. Okay? So now when I ask for cotangent of 135, okay, tangent is opposite over adjacent, right?
Yep.
So doesn't cotangent end up being adjacent over opposite? So you guys agree it's negative n over n, which reduces to negative 1?
Yep.
Is that something we can do?
Yeah.
Okay. Now let's see see here. Let's go to, I don't know if Desmos will be the best thing to do here. We'll see. So you guys haven't seen this stuff yet. Have you done any, I keep asking, have you done anything with those things in physics or any other science class you guys have been in? Okay, so that's a sine wave. That's how electromagnetic waves, that's how like your Wi-Fi works. That's how your radios work at home or in your car. That's how signals are sent. Does that make sense? If you guys ever seen an oscilloscope?
I don't know what that is.
Have you ever seen somebody like in a recording studio and they're like playing sounds and then you see on a screen things moving up and down like this? Or maybe on like a heart machine or an EKG at the hospital, you see things like this. What those things are doing are measuring electromagnetic waves, okay? An EKG or an EEG or something like that of your heart or your brain or whatever, okay? And then if you've got normal wave patterns, that means you don't have like brain trauma or whatever, okay? If you have like an irregular heartbeat, they'll be able to see that in the electrical signals of your heart, right? Does that make sense? And we display those using these. They're repetitive, so your heart cycle is repetitive. It's periodic. Brain activity is periodic. Sounds, okay? So sound travels through air, okay, or any medium in a like compression type process. What it does is, so the way that you can hear me is that, you know, I vibrate, my voice vibrates the air molecules or whatever, and it compresses them and expands them, and that allows then the sound to travel. So they're not, these are usually called longitudinal waves. Sound is a compressional wave or compression wave, but it's still modeled. Sound waves are still modeled using sine, cosine, and tangent variations. You guys ever heard of an amp? What's an amp do in music? Makes things louder. That number out front that I just used, that 3, is the amplitude of this thing. So when you see something that is stretched like this, okay, you're changing the amplitude, okay? What kind of radios do you have in your cars? What are the 2 frequencies? AM and FM. Do you know what the AM stands for? Amplitude modulation, okay? And it's basically that they change the signal by changing the height of these things, okay? So if I'm a radio station, I send out that signal, okay, that has a 2 out in front, that is a different signal than when it's a 1 out in front. Does that make sense? Okay? And then my radio on my car has a tuner on it that can decode those amplitudes, like 1150. Okay, so anything that has any wave that has like an 1150 amplitude, okay, when I tune my radio to 1150, my radio is going to decode that message and be able to play that music, okay, or that message. Do you guys know what FM stands for? Frequency modulation, okay? So when I look at this thing right here, would you guys agree that this thing repeats itself? This goes from 0 to like 6.28, okay? So that's 0 to 2 pi is one thing here, right? One rotation or revolution of this wave. If I change that number right there, does more of that happen between 0 and 6.28? Okay, now I've got more frequent, it's happening more frequently. It's going up and down more frequently, okay? So those are how signals are sent. So eventually, you will get to that, and we'll understand that. But let's look at the cotangent one real quick. Cotangent is that one right there, okay? Now, this is what I said. I don't know if Desmos, I don't know if this is going to be great to demonstrate. Maybe it will be. Negative 360. Yeah, this will be all right. The 360. Okay, so this is looking at the cotangent between negative 360 and positive 360. If I look at an x value of 135, that x value right there, does that make sense? At 135 is the cotangent being evaluated at -1. You get a y value there at -1, does that make sense? So that's why when I say cotangent of x, actually let's call this A. Now it's not going to show the picture anymore. But when I say A, we get that -1 right there. Does that make sense? And it's giving me the point then, let's say A comma cotangent of A. It's giving me that point right there. Is it okay with everybody? Would you guys agree that this point right here, and this one as well, and we'll talk about how we get that one, but this point right there, is that going to be the same kind of purple point? Does that make sense? Does it look like these like branches of this function are the same, just cut and pasted?
Yeah.
Okay. So if I take this one here, I'm just going to say I'm looking at A minus 360. Okay. So -225 would be the angle theta that I'm interested in, comma, now cotangent of A minus 365, or not 360, does it give me that same point? Does that point model that one? Does that make sense to everybody? Okay, so that is why when we say something like evaluate cotangent of 495, and we get -1, that we can say, well, it's the same thing as cotangent of 495 minus 360, because 495 is going to be right there, or maybe like right there. Okay, and then 135 would be right there. It's the same y value. Is that all right? Okay, so I want to make sure we kind of make those connections. Now, who's taking the ACT already? Okay, end of the ACT asked a bunch of questions about sine, cosine, tangent stuff, right? About 3, 4, 5 questions on there. Some of them are asking you to graph things, and they're coming up with a solution, and you don't know how to do that stuff yet, okay? But if we remember that if I want to find the solution to, like, say, cotangent of, so they say maybe y equals cotangent of x, or y equals cotangent of 135, or something like that, we can type that into our graph and see where those things cross, and that tells me the solution to that answer, right? So the hope is, obviously, we're going to be better at that test when you guys as juniors take it in February, because we'll have that stuff kind of under our belt by then. But the idea is, and I told my sophomores this the other day, if they understand that concept, that when I graph, or I want to solve an equation, and I want to graph the left side of the equation, the right side of the equation, and look at where they cross, that's the solution, I can probably do that ACT and be successful in a lot of the equations, if not all the equations, regardless of my exposure to them. Does that make sense? Okay.
When are you taking the ACT?
I think last class said February 20th. I haven't looked at that. 25th. So we got some things called trig identities here. Okay. I want to ask you. You've seen these before. Okay. Maybe not in trig, but you've seen them in algebra. Okay. If I have something like this, if I have 2x plus 7, okay, equals 1/2 of 4x plus 14. And I ask you to solve this. Now, if we're using the graphical aspect, you let that be y1, right? You let that be y2, right? Okay. Now and we know that, so the answer to it would be the x value, the answer to that equation is where the x value, where those things intersect, right? Or where they cross. If I'm doing it algebraically, I'm going to get 2x plus 7. What are you going to do over here to the right-hand side? Distribute. And you could stop right there because those two things are what? The same exact thing. Or, if you don't recognize that, you can keep going and say, okay, I'm going to subtract 2x from both sides. So we get 7 equals 7. You stop right there. Or you can go subtract 7 from both sides and you get 0 equals 0, right? Yeah. Each one of these situations, 1, 2, or 3, no matter where you stop, is a true statement, right? 0 equals 0 is true. 7 equals 7 is true. Always true. The one that says 2x plus 7 equals 2x plus 7 is always true when you choose an x value, right?
Yeah.
No matter what I choose for x here, it's going to be the same, and then I evaluate, it's going to be the same number over here, right?
Yes.
So no matter what you choose, x, this is going to be true. So if I were to graph these two lines actually coincide, right? They're the same line, right? Okay? So if you remember back to Algebra 1, if you were graphing a system of equations and it ended up being the same line, you say you had infinite solutions. You remember that? Okay? Systems of equations, systems of linear equations can have 0 solutions, 1 solution, or infinite. This would be an infinite. Those were identities. And what I mean by identity is, by definition, a mathematical identity is any equation that is true regardless of the input. Okay? Sometimes you might see it written as that it's a statement that is always true, or a statement that is always true for all inputs. Okay? Is that right? Okay. So we've got a couple here that we've seen, kind of messed around with a little bit. I'm gonna kind of make the argument that, do we feel comfortable with the reciprocal identities?
Yeah.
Okay. So those are always true. If I take the cosecant on my calculator and put a theta in there, and then take 1 over sine and put a theta in there as the same theta, should be the same result. So Desmos can demonstrate this with the graphing aspect. This does not work with, it doesn't work with the scientific calculator for Desmos. I don't know why they don't use the same coding, but so let's say I have cosine. Give me a let's just say A. Cosine A, and it'll ask me to create a slider. And now I'm going to say 1 over secant of A. Are those two numbers the same?
They are. No, they're not.
I don't know. So let's go. So I'm going to say A. So secant of A, 1 over cosine of A. All right, so those two values are the same, right? Left-hand side, right-hand side are the same for when A is 1. Doesn't matter what A is. No, okay? So these things are they're going to evaluate differently, right? No matter what you want to type in, they're going to evaluate to be the same thing all the time. Does that make sense? Okay, that's an identity, all right? One of the most important identities that we come across is these two, the tangent. Okay, tangent is equal to sine over cosine. We've already talked about that, right? Okay. So again, the argument, no matter what I want to type in, if I take tangent of A and then sine of A divided by cosine of A, no matter what I choose, unless it's 0, okay? It's not 0. Let's say, what is it? Cosine's got to be 90. So let's say I type in 90. Let's see what's going on. This must be, okay, so I think this is using, I don't know if this is using degrees. This isn't degrees. So let's say pi over 2. Okay, so they're the same, but they're undefined. They're not evaluated there. Okay, so it's because we're dividing by 0. Cosine of pi over 2 is 0. So that's why down here would be divided by 0, and that's why it's undefined. But regardless of what I type in here, do they evaluate to be the same? Okay, so those are identities. No matter what your input is, the outputs are identical all the time. So that's one we need to commit to memory, okay? If tangent and cotangent are reciprocals, does it make sense I could write cotangent this way?
Yeah.
That's just the reciprocal of the sine over cosine part, right? Okay. Let's talk about this guy right here. This is probably the number one formula that we're going to have to commit to memory. There's a couple different ways that we can talk about it and generate it. Okay. But let's do this real quick.
I thought you didn't like to make it memorize.
Well, that's why I'm showing you this, so you don't have to memorize it. You can, if you forget it, you can regenerate it. If this is theta, okay, if that's theta, I'm just going to work in the first quadrant, but this is true in any quadrant, okay? This point right here is an x comma y, right? Okay, so this distance here is x. That distance there is y, right? You guys remember calling this r? Okay, so let's say that cosine of theta, if you remember, cosine of theta, adjacent over hypotenuse, x over r, right? Sine of theta, y over r, correct? Let's make r 1. If r is 1, doesn't that mean that cosine of theta becomes just x? And sine of theta just becomes y. Does that make sense? If r is 1. So if cosine is equal to x, can I rewrite this as cosine right there? That distance is now cosine. Does that make sense? If sine is y, can I rewrite this distance as just sine? So now think about this. You got a triangle right now that is a right triangle. You said this distance is cosine theta. You said this distance is sine theta. And you say this distance is 1. If it's a right triangle, what's the number one theorem that works with right triangles? Pythagorean. So if I take sine and I square it of theta plus cosine squared of theta, so that's a squared plus b squared. Shouldn't that equal c squared?
Should.
What's c squared? 1. So just through some substitution things, we get this relationship, okay? Now, there's a notation thing here we got to pay attention to, and I talked about this in the last class, hopefully get to it tomorrow. Sine squared theta is this idea. It's sine theta times sine theta. Does that make sense? And we write it this way because, or we can write it this way. Does that make sense? Okay. But the confusion becomes, what happens if we write it this way? Now the theta is being squared. Okay. We don't want the theta being squared. We don't want, so if I have like sine of, let's say, 30 degrees, okay? Sine of 30 degrees is 1/2. Does that make sense? If I square this, what I want that to really do is square the 1/2. Does that make sense? And you get 1/4. When I write it this way, I'm squaring the 30 and making it sine of 900, which does not turn out to be 1/4. Does that make sense, everybody? Okay. So it's just a notation thing that we pay attention to. So to eliminate that confusion, we write the square after the word. Okay. But you can write it this way. Those two things mean the same thing. Okay. My hope is that we remember that, okay? That's going to be the number one identity that we focus on throughout this course. A lot of these two come from it. So if you were to add to the last class, if you were to ask me today at 8:15, say, what is tangent squared plus 1 equal to? I'm not going to know right off the bat. I'm going to jot something down real quick and then tell you, well, it's secant squared. I knew it was either secant or cosecant. I just wasn't sure, okay? Because I haven't memorized it, because I think my memory's going to fail. I know my memory's going to fail me, right? Okay? But if you were to ask me, what's sine squared plus cosine squared equal to, I automatically know that's 1 because it's like 2 times 2. Okay? It should be something eventually that we are comfortable. Do you guys remember what's the formula for a circle?
Yeah.
You You remember this?
Yeah. Who's the pirate?
Okay. Now when we look at a circle, the formula for a circle, in this case, we're going to be centered at 0, 0. So the h and k go away. So we get x squared plus y squared equals r squared. Now we're interested in r being 1. When r is 1, it's a radius of 1, right?
Yep.
It's a unit circle because the radius is 1. X squared plus y squared, we just said x was the same thing as cosine. Y was the same thing as sine. So that's another way of generating that formula. Okay? But no matter what you do, when we look at this here, if I go sine squared of A plus cosine squared of A, what's it equal?
1.
Equals 1, no matter what I choose, right? Now, I want to show you that if it was 2A, now it all evaluates differently, right? So that's not an identity. But if it's 1A, that's an identity, okay? Now let me show you the graph real quick. We'll get to, so that should make sense. Does that show you that the y value is always 1 then?
Yes, sir.
Okay. So that's maybe an alternative way of writing the equation y equals 1. Okay. We're going to work a lot with that thing. Okay. So sine squared plus cosine squared equals 1. It's obviously addition is commutative, so you can go cosine squared plus sine squared equals 1 as well. We'll pick up with that tomorrow. Tomorrow will be an introduction to our first set of analytical trig, where we're looking at an equation or expression, trying to rewrite it in terms of another one.
We're gonna get
Okay.
tomorrow.
What's tomorrow? Thursday?
Yeah.
I'll probably open something, but it won't be due till maybe middle next week.
How you do?
What are you saying?
Is this one still gonna be Friday?
Well, yeah, we've had since Monday.
It's Monday. Yeah. I have a life outside of Thursday. Tuesday.
So do I, Blaze, but I'm always ready to go. I never come to class and say, hey guys, I need 45 more minutes. You guys just chill. You would be fine with it, but I don't do that,
Pardon
right?
the interruption. This is just an announcement for those planning to attend the gatekeepers meeting.